this lecture, we are going to talk about methods for calculation of the Clebsch-Gordon coefficient. In particular, I will be describing one particular method in this lecture. In the next lecture, we are going to talk about an alternative method. But before we go there, let me just remind you exactly what the Clebsch-Gordon coefficients are. You may remember these quantities here, the kets with rounded end brackets that we had written down. This is a notation that we are using here. These are eigenstates of j square, jz, j1 square and j2 square with the eigenvalues j into j plus 1 h cross square, etc., etc. They can also be expanded in terms of the other eigenkets that are of relevance in this problem. Remember, we are talking of two systems together making up a composite system, and the first system has spin j1, the second system has spin j2, and the natural basis is the direct product basis, which is just j1 j2 m1 m2, which simply means that the j1 m1 here are eigen values, or at least stand in for the eigenvalues for j1 square j1z, and j2 m2 stand in for eigenvalues of j2 square and j2z. And this forms a complete basis of our direct product space. So it's natural that we should be able to rewrite these vectors, which are eigenstates, are the simultaneous eigenstates of j square, jz, j1 square and j2 square, in terms of these vectors. And the coefficients in blue here are simply the Clebsch-Gordon coefficients. And let me also remind you that we had adopted a shortened notation. We would drop the j1, j2, which is there on both sides of this notation often, but we will have to keep in mind that j1 and j2 labels are very much there, especially when we are dealing with calculations. We also had established two very important properties of the Clebsch-Gordon coefficient. At least we had established one of them, and we are going to establish the other through the derivation or the calculation of the Clebsch-Gordon coefficients that we are going to do in this lecture. The first property was that unless this label m, which is the eigenvalue of jz, matches m1 plus m2, the Clebsch-Gordon coefficients would vanish. And the second property said that unless this triangle inequality here is satisfied, the Clebsch-Gordon coefficient would also vanish, which essentially starts out by saying that the largest possible value of j can be j1 plus j2. We will now outline a method by which we can calculate all the Clebsch-Gordon coefficients, and this is going to be a rather long and admittedly tedious process. So I am going to show you the steps, work out some of the steps explicitly, but I would expect all of you to actually work with your pen and paper and establish that all the steps that I am writing down are correct. So let's begin with that. The first thing we realize is that since the largest possible value for m1, which runs, remember, from minus j1 to plus j1, can be j1, and the largest possible value for m2 can be plus j2, the largest possible value of m allowed is just j1 plus j2. Right? No other value larger than this is possible. And this immediately tells me that the largest value possible for j also has to be j1 plus j2. After all, if j's largest value were less than j1 plus j2, then it would not be possible to have an m which takes a value j1 plus j2. And if j's largest value was larger than this, then you would definitely get an m which, remember, runs from minus j2 plus j, which is larger than j1 plus j2, and as we have seen, you cannot have an m larger than that. After all, m has to be m1 plus m2. So we have established that the highest weight state of this direct product space, and that's a technical term, but it simply means the state with the largest eigenvalue for jz is j1 plus j2, and in fact it's simply this state. j1, this notation may look a bit confusing, but notice that what we are saying here is that this is the only state which is an eigenstate of j1 square, j1z, j2 square, j2z, which will give me this possible eigenvalue of j1 plus j2 for m, is nothing but this state. And just to remind you, these are actually the J square labels. These, despite be looking the same, are actually JZ labels, and we shorten the notation by dropping the J square labels, and because they are always J1, J2, but they are the JZ labels are also J1 and J2 for this particular state, and there is only one state which does this. So we know that the state which has J1 plus J2 eigenvalue for Jz, notice there is a rounded bracket, so this talks about J square Jz eigenvalues, not J1 square, J1z, etc. And this state can only be equal to J1, J2. Of course, you might have noticed that we are sort of being slightly inaccurate here, in the sense that after all, it were very possible that these two states might differ by a phase factor. So what we are doing here is that we are establishing a sign convention or a phase convention, that we are going to say that this state is J1, J2. We have chosen the phase here. Anyway, any overall phase is physically useless or has no physical significance, so it doesn't really matter. This is a convention which everybody uses. Now that we have found out the highest weight state, J1 plus J2 comma J1 plus J2, and that's nothing but J1 J2 here, we can find out the next state, which is we just apply J minus, which remember is J1 minus plus J2 minus on both sides. And let me remind you once again that this notation hides the fact that J1 minus is really J1 minus direct product with I2, and J2 minus is really I1 direct product with J2 minus. So we apply this on both sides, and what happens? We keep on, this actually keeps on reducing the J1 plus J2 eigenvalue, and keep on doing this until we reach minus J1 minus J2, which is the lowest possible eigenvalue for Jz, given J square as an eigenvalue J1 plus J2. Any further attempts to lower this any further by hitting J minus will make the ket vanish. So this way, what we have got is we can get, by applying J minus successively, are all the states corresponding to J square eigenvalue of J1 plus J2 into J1 plus J2 plus 1 H cross square. And there are exactly twice J1 plus J2 such states. Now to proceed further, we need to go to the next J value. Remember, we have already established that J values cannot be more than J1 plus J2. So next J value has to be J1 plus J2 minus 1. And the highest weight state for that, of course, is the one for which Jz value is also J1 plus J2 minus 1. So how do we get this? Now, unlike the previous case where the only possible way to get J1 plus J2 comma J1 plus J2, especially note that the only possible way to get Jz eigenvalue to be J1 plus J2 was to choose J1 and J2 as the eigenvalues for J1z and J2z respectively. But now I want the Jz eigenvalue to be J1 plus J2 minus 1. So this can be achieved by linearly combining this one, J1 minus 1 and J2, and this one, J1 and J2 minus 1. So there are two possibilities. So this fact alone, the fact that the eigenvalue for Jz is J1 plus J2 minus 1, is not sufficient to tell you exactly what the state is, unlike here. Here, up to a phase factor, you knew for sure that the state has to be J1, J2, because there's only one way to get J1 plus J2 as a Jz eigenvalue. Here there are two different direct product eigenstates, J1 minus 1 comma J2 and J1 comma J2 minus 1, which will both give you the same Jz eigenvalue. So our state, J1 plus J2 minus 1 comma J1 plus J2 minus 1, must be a linear combination of these two states. How do you find out which linear combination? Well, remember when we went through this and applied J minus, the very next step that we got was J1 plus J2 comma J1 plus J2 minus 1. Now that's, if you compare that state with this one, they correspond to different eigenvalues of the Hermitian operator J square. One this one corresponds to J1 plus J2 into J1 plus J2 plus 1. This one actually corresponds to J1 plus J2 minus 1 into that number J1 plus J2 minus 1 plus 1. There's of course an H cross square. This means that these two states must be orthogonal, and using that we can figure out exactly which linear combination of these two states here are we talking about. So you choose it to be orthogonal, you have found out exactly what state you are dealing with. Now again, there is a phase factor at work here, but that phase factor is also an overall phase, does not really matter as far as the rest of physics is concerned. We keep on applying J minus to this until we go all the way down to minus J1 plus J2 minus 1, that is minus J1 minus J2 plus 1 for the Jz eigenvalue, and that's where we stop with this particular state. Then we move on to J1 plus J2 minus 2 and so on and so forth. If you keep track of exactly how many states you are getting, you will be able to show that by the time you get to J1 difference J2 and find out all the states corresponding to that, you have found exactly twice J1 plus 1 into twice J2 plus 1 states, which means that you have found out all the independent states that there can be in this particular problem. Remember, we built up our direct product space by taking a direct product of a 2J1 plus 1 dimensional system H1 for the system A, and then the twice J2 plus 1 vector space for the system B. So the direct product is 2J1 plus 1 into 2J2 plus 1 dimensional. So once you have found out all the possible eigenstates, you have counted them and found out that you have got exactly this number, you have found out all that there can be. This is actually one way of establishing the triangle inequality that we talked about. Once we start with J1 plus J2 and go all the way down to J1 difference J2 for the J square eigenvalue, we have exhausted all possible independent states. So there can be no more. So let's put this idea to action for a particular example. So we will talk about a particular example. We will take J1 equals 3 and J2 equals 1. Notice this is going to be a pretty long calculation, especially if I do it in gaudy detail, because J1 equals 3 means there are in the subsystem A, the Hilbert space was 7 dimensional, 2 into 3 plus 1, and the subsystem B was 3 dimensional. So we have a direct product space which is 21 dimensional, so there are 21 vectors of the form Jm to be found. So quite a long calculation. I am not going to show you all the gaudy details, but I am going to show you enough details for you to be able to work out the rest yourself. So the highest wave state must be when J1 M1 takes the value 3 and M2 takes the value 1, which is M takes the value 3 plus 1 equals 4. So our state here is 4 4 and this must be 3 1. Let me remind you, this 4 4 really is 3 1 semicolon 4 4, and this 3 1 is 3 1 semicolon 3 1. Just to remind you, the rounded brackets are J1 square, J2 square, J square, Jz eigenstates. The angular brackets, the standard ket notation, is J1 square, J1z, or rather J1 square, J2 square, J1z, J2z, in that order, the order in which we write it. Of course, we are omitting the 3 and the 1 which comes from the J1 square, J2 square, which are there on both sides. But we will, as and when necessary, we are going to invoke the full notation just so that you can get all the details of the calculation clearly. So we apply J minus on both sides. So what happens when I apply J minus on the left? Here what we have done is we have written down 4 4 in its full glory. That is, we have included the J1 square, J2 square, J1z, J2z notation, J square Jz eigenvalues. But what is important is J minus acts on this 4 4, reducing the 4 to 3 and gives you this factor. Just to remind you, J minus's action is root over J plus n into J minus m plus 1 into h bar into the ket with one value reduced. There's an h bar missing here. Of course, you might argue that I am using h bar equals 1 here or whatever, but this was really an honest mistake. I forgot to type the h bar there. So j minus 4 4 is simply root 8 times 4 3. What happens to the right hand side? Well, the right hand side, let's now write it out in full glory. Right hand side was j1 minus plus j2 minus, but this really meant j1 minus direct product with I2 plus I1, the identity in the first space, direct product with j2 minus, acting on the state 3 1 really was 3 1 3 1, right? j1 square, j2 square, j1z, j2z. So what happens? This really is, okay, it's even clearer if we break it up into the direct product notation. 3 1 3 1 really means 3 3 for j1 square j1z. This is pertaining to the subsystem A, and for the second subsystem, the one labeled 2 below here, the state really is 1 1. So this is really what we are talking about. Now once you get used to it, you will be able to do this in your head without writing it out in full. But if you are doing this for the first time, I strongly advise that you break it up in and write the whole thing, so that you don't get confused as to what's happening where. Now this of course will give you two terms, one with j1 minus I direct product I2 acting on this direct product state, the other with I1 direct product j2 minus acting on the direct product state. Now this gives you these two terms. After all, when j1 minus direct product I2 acts on 3 3 direct product I1 1 1, is j1 minus acting on 3 3 direct product with I2 acting on 1 1. This is exactly how direct product operators work. And what about I1 direct product j2 minus acting on 3 3 direct product 1 1? Is I1 getting to act on 3 3 and j2 minus getting to act on 1 1. Now I know what j1 minus does to 3 3. It changes it to 3 2 with a factor in front, which is root over 3 plus 2 into 3 minus 2 plus 1 times an h bar, which we have put equal to 1 for this. I2 1 1 is of course 1 1 itself. This is 3 3. This one is root over 1 plus 1 into 1 minus 1 plus 1 times 1 0. So if you use all that, you get root 6 3 2. That's what j1 minus 3 3 does. Direct product with 1 1, of course I2 does not change the 1 1. Then 3 3, which is I1 3 3 here, and j2 minus 1 1 is root 2 1 0. So combining them all together, what we get, remember this 3 2 1 1 is in our notation is 3 1 semicolon 2 1, and this one is 3 1 semicolon 3 0, and we will just drop the 3 1 from both sides. So we get root 8 4 3, which is the left hand side, must equal root 6 2 1 plus root 2 3 0. So at the end of the day, this gives me what 4 3 is, just by dividing through. So the idea is pretty straightforward. All you have to do is keep track of where every one of these square root of j plus m into j minus m plus 1 factors are going. By the way, even if I had included h bar in the calculation, there would have been h bars on both sides, so they would have simply cancelled out. So the final result would definitely be this. So what are the Clebsch-Gordon coefficients? There are two Clebsch-Gordon coefficients here. One is this 2 1 4 3, which is root 3 by 4. The other is bar 3 0 ket 4 3, that's root over 1 by 4. So two non-zero Clebsch-Gordon coefficients that we have found out at this level. We of course had already found out one Clebsch-Gordon coefficient here, which was simply 1. Okay, now, so these are the two things we have. Let's try one more. We apply j minus on both sides. This time I am going to be a bit quicker. This 4 3 becomes 4 2 by application of j minus. That's root over 4 plus 3 into 4 minus 3 plus 1 on this side. And on the other side, remember what you have is root over 3 by 4, then j1 minus plus j2 minus, which is j1 minus cross identity plus identity cross j2 minus, acting on the state 2 1. 2 1, remember, is actually 3 1 semicolon 2 1, which actually is the state 3 2 direct product with 1 1. Listening to me may be not very convincing right now. It's much better if you wrote it down and did it yourself. But all I want you to realize is that when you apply this is root over 3 by 4 times the first term, and you have in addition root over 1 by 4 times this. So root over 1 by 4 times this whole thing, and the rest works out in a pretty straightforward manner. J minus 3 2 will give you 3 1 with a factor in front. We have to figure out exactly what that factor is. J2 minus 1 1 will give you 1 0, and so on. And if you carry out this calculation, this is what you are going to get. I put in all the factors here, hopefully correctly. You should check on your own. But notice, this is really this 1 1 here. Is this correct? The answer is it is, because 3 2 becomes 3 1 and the 1 1 stays 1 1. And if you drop the 3 and the 1 label, you get 1 1. Similarly here, 3 2 stays 3 2. This becomes 1 0, and again dropping the 3 and the 1 label, you get 2 0. It takes a bit of getting used to this. Here, for example, 3 3 becomes 3 2. This stays 1 0. So dropping the J1 square J2 square labels once again, just to make this thing fit into the screen. What we get is just 2 0, and so on. So you have to be a bit careful. This one here, the first one here actually comes from this one, after J1 minus has acted on it, reduced it by 1 of course, and the next one comes from this. Here 2 comes from this one, and 0 comes from what happens after J2 minus acts on this one. And after we collect all the terms together and divide through by root 14, this is the final result that we have. Just a quick check that this is not completely absurd. If you just square and add all of this, which is, we add 15 by 28 to 3 by 7 and 1 by 28, that's of course 15 by 28 plus 12 by 28 plus 1 by 28, that's actually 1. So you started with a normalized state and you are getting a normalized state. That's exactly what you are supposed to get. Just to remind you, these complicated factors in front really was to ensure that the normalization stays intact after you hit with J minus. So now we have 3 non-zero Clebsch-Gordon coefficients at this level. And continuing this way, this is a homework. You should really check that this really works for all the cases. This will test your surd handling abilities a bit, but frankly is all well within reach of class 10 level algebra, or frankly arithmetic. By keeping on applying J minus, we have already worked out the first 3 here, but keeping on applying J minus, we will get 4 1 4 0 4 minus 1 all the way down to 4 minus 4. And once we have got there, we have got exactly 9 states. So remember, we are dealing with 21 dimensional vector space, and we are actually going in from the original direct product basis to a new basis, and we have now found 9 vectors in that basis. So there are 12 more to go. So we need to start with 3 3. Remember, we started with 4 4, which we knew was 3 1. We cannot have a J more than 4 here with J1 equals 3, J2 equals 1. 5 is out of the question, because then of course I would have had a m equals 5 as well, which you simply cannot get with J1, with m1's largest value being 3 and m2's largest value being 1. So we need to start with 3 3, and this must be a combination of 2 1. These are, remember, m1 and m2 values. 2 1 are the only 2 1 and 3 0 are the only 2 ways you can add up m1 m2 to get 3, the jz eigenvalue. Remember, you are not allowed to have a m1 more than 3 or an m2 more than 1. So this is what you are going to get. And what is that linear combination that we are looking at? It has to be orthogonal to 4 3, which we had already figured out a while ago, has to be this. Now, because this is a linear combination of just 2 kets, it is actually trivial to write down what 3 3 is going to be just by taking a look at it. All you need to do is swap these 2 coefficients and change the sign, and that's it. That will make these 2 things orthogonal. Of course, if you were dealing with complex factors here, you would also have to conjugate, but right now you don't have to worry about that. So it's easy to see that all you do is swap the coefficients, change the sign in between, but you have two choices. You can have +1 or -1. Does it matter which one you are going to pick? Well, the overall sign, as we said, does not matter physically at all. However, if you are communicating with other people, especially if you are writing to a scientific journal, for example, it's important that your choice of signs don't really differ from another person's, so that you can all be on the same page, so to speak. So scientists who deal with angular momentum radiation regularly, which includes people who deal with quantum physics, of course, but also people who deal with atomic physics and many other branches, condensed matter, so on, they usually adopt a sign convention so that that everybody can agree upon. Well, that's actually easier said than done, because depending on which author you are reading, there are quite a few sign conventions which apparently everybody agrees upon, which is absurd. So the one which most people use, I guess, is the Condon-Chatelet convention. So this sign convention which everybody agrees upon, hopefully, is the one which you should really be using if this were professional work. Right now we are not going to bother too much about that. We are just going to choose the plus sign here. This Condon-Chatelet condition, which are the most often accepted sign convention, although there are people who don't like it, would say something definite about the plus or the minus sign here, but I am feeling too lazy to look that up. And more importantly, the sign convention is just that, it's a sign convention. It does not detract or add anything to the basic overall physics. So now that you have got 3, 3, you apply J minus successively to it. So you can get 3, 2, 3, 1, 3, 0 and so on, and you get these 7 states. Again, this is something which you should check out on your own. These are, well, let me warn you, this is not going to be a very small calculation. It's not very tough, but it takes a lot of time, and it also tests strongly whether you can handle your surds, square roots, etc. properly. But one thing, at any given stage, if you were to square and add all the coefficients, you must get 1. That's a good way to check whether you are going right. So now we have 9 plus 7 independent states, 16 of them, 5 more to go. So what you need is 2, 2, right? We have done J equals 4, J equals 3. Now the next possibility is J equals 2, and the highest base state for that is 2, 2. Notice that if I manage to apply J minus successively on that, we will go all the way down to 2 minus 2. That's exactly 5 more states, and we have managed to find 21 independent states. These, remember, are independent because they all differ from each other by at least one eigenvalue of one of the 4, in fact, of J square or Jz, in fact one of the 2, and that's enough to make it. Or since J square and Jz are Hermitian operators, eigenvectors differing in at least one of their eigenvalues must be orthogonal. So we have 21 orthogonal vectors here in a 21 dimensional space, so there can be no more. So this actually says that all possible J values must run from 4, 3 and 2, and you can't get any more beyond that, which of course is completely consistent with the triangle inequality which we quoted. J1 plus J2 is the largest possible value, and J1 difference J2, in this case 3 minus 1 equals 2, is the smallest possible value of J. And you can easily check that this works no matter what J1 and J2 you use. So now of course we need 2, 2. How do we get 2, 2? Well, we get 2, 2 by linearly combining 1, 1. Remember, these are M1, M2 values. So we need to look for M1 plus M1, M2 such that M1 plus M2 add up to 2. So 1, 1, 2, 0 and 3 minus 1 are the only possibilities. You can't get 0 here because 0, 2 is impossible. J2 being 1, M2 cannot be more than 1, and so on. So these are the 3 vectors which add up to this. So of course, how do you find the ABC coefficients? The way we are proceeding, we would find them out by insisting that 4, 2, which is also made up of these same 3 vectors, gets must be orthogonal to it because they differ in the j squared eigenvalue, and C2 must be orthogonal to it. So this gives us two equations for A, B and C. You might be wondering why we are focusing only on 4,2 and 3,2 and not on the other 16 states that we had found so far, or the other 14 states that we had found so far. The answer is, well, if you tried those, you would see that they would give you trivially 0 equals 0. Only these two actually, where 4,2 and 3,2 are the only ones which use the same kets, 1, 1, 2, 0 and 3 minus 1. So you get non-trivial equations here for A, B and C, and by solving those equations, of course you have two equations in 3 unknowns. These will not give you unique values of A, B and C. To pin down what the values of A, B and C, you have to use one more condition, which is normalization. Up to an overall constant sign, plus or minus, this is what you get, and we can start with 2, 2, then apply j minus successively, and we will get 5 more states, and we will be done. So it's up to you. Please work out all the details. Now, this is a perfect approach if you want to find all the Clebsch-Gordon coefficients corresponding to a particular J1 and particular J2. In fact, this is the only efficient way of doing that. However, sometimes you may not really want all the coefficients, you may want only one of them. Let's say all the coefficients corresponding to 2, 2. Let's say you want to expand 2, 2 in this form and you want to find out the values of A, B and C, and just that. How would you do that? It's really a waste of time to work through all the 16 states before this and then work this out. Actually, you might have noticed that you didn't really have to work through all the 16 states. You can, if you all you ever wanted to do is find 2, 2 by this approach, you may drastically be able to figure out how to cut down your work, but still it's a lot of work. So we will talk about another method in the next lecture by which you can figure out the expansion of one such eigenket in terms of the direct product eigenkets. So if you wanted only 1 or 2 Clebsch-Gordon coefficients, the other method may be more efficient. So that's the subject for the next lecture. This method is not efficient if you wanted to find the expansion of one state only. In the next lecture, we will figure out a way of working out the expansion for one state only, this particular expansion, the values of A, B and C, without referring to any other of the previous states that we have worked out, and we will find an efficient way to find that out, and we will do this as an example. So for the time being, I would just ask you to go through this with pen and paper and try to do the whole thing. Okay, it might be pretty boring to do the whole thing, but do as much of the calculation as you can do without dying of boredom to ensure that you have understood the thing clearly. I cannot really give you a guarantee that this is going to be exhilarating work. It's tedium, but it's an important thing to work out. So please do that.